Hello everyone, today let's take a look at QP 109, looking at some important stuff. It's going to be Pascal's identity and Pascal's triangle. So first let's show this identity using committee forming argument and then algebraically, and then we're going to use it to construct Pascal's triangle. So let's do part A first. So first on the left side of this equation, we're saying n choose k. So if we have n different people, which I'll draw a bunch of stick figures over here. So let's say I have n people over here and I want to choose k of them to be in some type of committee or group. So let's just say in this example that I have 6 different people and I want to choose 3 of them to be in a group. I have 6, choose 3 ways to do so. They're going to look something like this. I could choose these 3 people to be in a group, or I could choose these 3 people, or I could choose these 3 people, etc. So that's what the left hand side of this equation is saying. And now on the right hand side, we're basically taking n minus 1 choose k plus n minus 1 choose k minus 1. So what does that mean? Basically what this is saying, I'm reducing the number of people that I'm talking about to n minus 1 here. So I'm basically excluding one person from the group and I'm just looking at the remaining n minus 1. So in this case, when I had 6 people, I split my group into 2 different parts. This guy over here as a solo and then a group of 5 over here. And I still want to find the number of ways that we can form a committee of 3. So for this term on the right hand side, n minus 1 choose k, well, we're looking at our group of 5 people in this case, and we're saying how many ways can we choose k of them to be in a group out of these 5 people. So in our case, k was 3. And then within this group of 5, I can form a committee of 3 by taking these 3 people, or I could take these 3 people, or I could take these 3 people. So we're going to have 5 choose 3 total ways to do that. So if we call this lone guy over here Bob, this term right here represents the number of ways that we can choose a committee that excludes Bob from it, right? Now for this term over here, again, I'm looking at the group that does not include Bob, so this group of 5 over here, and instead of choosing k, now I'm choosing k minus 1. So in this case, I'd be choosing every group of 2 people. So what are my possible options? Well, I could choose these 2, these 2, these 2, these 2. I'm going to have 5 choose 2 ways to do that. And then for every group of 2 that I choose from the set that does not include Bob, I can just add Bob to that set and then I get a committee of 3. So if I choose these 2 people and then I add Bob, I choose these 2 people and then I add Bob. So this term over here represents the number of committees that do include Bob, right? Because every time I choose a group of 2, I'm leaving a spot open for Bob to take, right? Okay, so this first term on the right-hand side represented the number of ways to choose a committee of k such that Bob is excluded from our group. And this term over here represents the number of ways to choose a committee of k such that Bob is included in our group. And for any given group, either Bob is going to be included or Bob is going to be excluded. There's no other option, and these sets are also disjoint. So when we add these up, we're just going to get the total number of ways that we can form a committee from these 6 total people, or these n total people in the general case. Our example, we had 6 choose 3, and we were saying that that was equal to 5 choose 3, and then we were saying plus 5 choose 2. So we had 5 choose 3 committees that Bob was not on, and we did 5 choose 2 committees that Bob was on. And when you work out 6 choose 3 is equal to 20, and 5 choose 3 is equal to 10, and so is 5 choose 2. So it works out. So now let's actually show this identity algebraically just by writing out the definition of the choose formula, right? I'll write it down here. This is what I get when I do that. You notice this term in here can be simplified. I'm going to distribute this negative inside, and when I do that, this is just going to be n minus k factorial, like so. Let me move these over. Okay, now let's get this right-hand side to look like the left-hand side. In order to do that, I need to add these fractions, so I need to find a common denominator. You notice that I can do that by multiplying top and bottom here by n minus k. Since we want an n minus k in the bottom, right, we can multiply this side by n minus k and on n minus k. Okay, so when I do that on the bottom, this is going to simplify to n minus k factorial. So we almost have, I mean, we have these terms correct, but we need these terms to be the same. So what we can do is multiply top and bottom of this side by k, and then we're going to get a simplification down here to k factorial. Now we have a common denominator, so I can add up these fractions. You notice that when I do so, I'm going to get something that looks like this right here. Then when I distribute that n minus 1 factorial inside of this n minus k term, we're going to get n times n minus 1 factorial minus k times n minus 1 factorial, but we have an n minus 1 factorial times k that we're adding here, so these are basically going to cancel, and then on top, we're just going to be left with n times n minus 1 factorial. Then n times n minus 1 factorial is just going to be equal to n factorial. So there we've shown that the right-hand side and the left-hand side are algebraically equivalent. But the best way to think about Pascal is going to be the committee way, where we're just choosing one of our people to be excluded, counting the number of committees we can form that way, and then we are including them and counting the number of committees that we can form that way, and adding them up. Since they're disjoint, they're going to sum to our total n choose k. Now let's just construct a few rows of Pascal's triangle. In part A, we were talking about 6 choose 3. We found it was equal to 5 choose 3 plus 5 choose 2. So let's just start with that. Well, we knew that 6 choose 3 is 20. And then basically what we can do is say that it is the sum of 10 and 10, 5 choose 2 and 5 choose 3. So this term over here represents 5 choose 3, and this one over here represents 5 choose 2. And when we sum them up, we get this term of 6 choose 3. And now we can recursively just apply this going backwards. So recursively, if we apply this, we know 5 choose 3 is just going to be equal to 4 choose 2 plus 4 choose 3. That's because if we say Bob is one of our 5 people in our group of 5, then we can choose a committee without Bob in 4 choose 3 ways, and we can choose a committee with Bob in 4 choose 2 ways. 4 choose 2 is equal to 6, 4 choose 3 is equal to 4, so I can break down 10 into the components 6 and 4. This is 5 choose 3, this is 4 choose 2, and this is 4 choose 3. Now 5 choose 2, I can use the same identity to break it down into 4 choose 1, and then I'm going to have 4 choose 2, right? When I add those up, this is 6 and this is 4 again, so I break these down into 4 and 6. Now you notice this term is 4 choose 1, this term is 4 choose 2, this term is also 4 choose 2, so we can just combine these into one single number, right? They both draw from this number, and then this one over here is 4 choose 3. Now I can break down this 4 choose 3 over here into 3 choose 3 and 3 choose 2. When I draw those out, I know 3 choose 3 is equal to 1. I'm going to have that over here, and 3 choose 2 is going to be equal to 3. Now this one right here, 4 choose 2, I can express that as 3 choose 2 plus 3 choose 1. This is my 3 choose 2 term right here, so it draws from this one, and then my 3 choose 1 I haven't drawn in yet, but it's also going to be 3. You can see 3 plus 3 is 6. Everything is checking out here. Now this term over here, which was my 4 choose 1 term, I can break that down into 3 choose 1 plus 3 choose 0. I already wrote out my 3 choose 1 term over here, so it's going to draw from this one, and then 3 choose 0, which we know is equal to 1. This is 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3 right here. Let me make some more room so we can keep going. This term, although it doesn't make a lot of sense, it's going to be 3 choose 0, can break down into 2 choose 0, and basically 2 choose negative 1, which we're just going to call this as 0. So this is going to be a 0 here. 2 choose 0 is equal to 1, so we're going to have a 1 here. 3 choose 1 can be broken down into 2 choose 0 plus 2 choose 1. 2 choose 1 is 2. This 3 choose 2 term can be broken down into 2 choose 1 plus 2 choose 2. 2 choose 2 is 1. And then this 3 choose 3 can be broken down into 2 choose 2 plus 2 choose 3. Again, this term doesn't make any sense, so we're just going to call that as 0. And now you can see the pattern, right? I erase all this stuff. Every single term in our diagram is just going to be the sum of the two things that are connecting it, right? So for instance, this one right here, the sum of 10 and 10. This one, the sum of 6 and 4, etc. So this row here, 2 choose 0, 2 choose 1, 2 choose 2. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Now visually you notice the pattern. This row is going to correspond to 4. We know 4 choose 0 is 1. We already have 4 choose 1, 4 choose 2, and 4 choose 3. And then 4 choose 4 is also going to be 1. Now I'm just adding the two previous terms. So for this one right here, I have 4 plus 1, 5. I'm going to have a 1 on the outside because 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, and then 5 choose 4 is going to be 4 plus 1, 5. And then over here, 5 choose 5 is 1. Now for our row of 6, 6 choose 0 is going to be 1 again. You can see this whole outer diagonal is going to be 1s because when you choose 0 from anything, it's going to be 1. And then here I'm going to get 6 choose 1. So I add 1 plus 5, 6. 6 choose 2 is 10 plus 5, 15. 6 choose 3, we already did, is 20. 6 choose 4, 10 plus 5, 15. 6 choose 5, 5 plus 1, 6. And then 6 choose 6 is 1 again. That's what Pascal's triangle starts to look like. You can essentially exclude these zeros because you can't choose anything that is a negative number, and you can't choose anything greater than the number that you are choosing from, right? So let's just do it all the way up to the top. Now we have rows for 6, 5, 4, 3, 2. Let's just do it for 1. We know that 1 choose 0 is 1, and 1 choose 1 is also 1. You can see that these all add up, and it makes sense. And finally, 0 choose 0 is 1. So at any point in this triangle, we're just using the identity that n choose r is equal to the sum of n minus 1 choose r minus 1 plus n minus 1 choose r, like so. And then you can recursively just keep going backwards and forwards using that same identity on this one, same identity on this one, and that's exactly what we did here. There's a lot of unique stuff going on with this triangle that I'm sure we'll talk about later. There's a lot of identities, hockey stick identity. You can think about it in terms of path walking and etc., a bunch of stuff like that. You can also extend this triangle and keep it going on forever. For instance, all I have to do is add up the previous terms, and then this is going to be for my row of 7, right? So right here I have 7, 1, this is 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3. This is going to be 7 choose 4 over here, 7 choose 5 over here, which is going to be 21, and then 7 choose 6, 7 choose 7 is going to be 1. So again, general form of this triangle is going to look like this. If you actually break it down one more time, this would go to n minus 2 choose r minus 2, and then we have an n minus 2 choose r minus 1, and then you can see that this is going to share one of those terms in common when you break it down. It's going to have n minus 2 choose r minus 1 and n minus 2 choose r exactly. This right here is really the core thing that is going on. It's going to be this little action right here, right? And you just keep on going out and you can do it forever.